Hello, hello. Here we go on podcast 2 of week 11 for Chem 30. This podcast is going to build, of course, on what we've already been doing, but it's also going to come back to a Chemistry 20 concept that we haven't talked about in quite a long time, and that's of acid-base indicators. And I love acid-base indicators and their simplicity and their colorfulness. It brings out the artist in me. So, guys, some of this, like I said, is going to feel like a review in terms of our analysis of trying to figure out the pH of a particular solution, both qualitatively in terms of color analysis and quantitatively in terms of actual number analysis. So anyway, let's get right into it. Now, something that you didn't likely get as introduced to last year, it wasn't as reinforced. I know I don't spend a massive amount of time in it, that ultimately what indicators are mixtures of weak acids and their conjugate base. So ultimately what we have here is indicators themselves are equilibrium type situations where if you add an acid to an indicator, it will shift it one way, and if you add a base to an indicator, it will shift it the other way. The only thing that's unique about indicators is that the shifts are really easy to notice because they're associated with color changes. Now we've got two forms of indicators that are recognized. This is one form, and that's the acid form. Why? Well, think about what we talked about in the previous podcast with the Bronsted-Lowry acids and Bronsted-Lowry bases. Definition of a Bronsted-Lowry acid is something that can donate a proton. So naturally then, this is the form that has a proton to donate. Vice versa, the base form of the indicator we represent this way, right? This is just a general formula, if you will. This one has the ability to accept a proton with its negative charge. Hence, it is a Bronsted-Lowry base. And ultimately, as I mentioned before, the key distinction here is there's a color difference between the two. That's what makes indicators so useful from a qualitative analysis perspective. Alrighty, let's keep going here. Now, just a quick reminder about a few different indicators for you, right? This is just showing you some very, very common ones. It's certainly not all the indicators in the world, but we've got the universal classic one. We move into, I'll just pronounce these for you because a lot of people struggle with the pronunciation. We've got phenolphthalein, super common indicator, methyl orange, thymol blue, bromothymol blue, phenol red. Chances are you worked with a lot of these last year when you were able to try a few different indicators in a variety of acidic or basic or neutral substances. Now, guys, when we put those simplistic formulas into an equilibrium system, what you can see is the logical, let's just change the color of this thing, where the hydrogen is being donated from the acid to what is acting as the base, in this case, our water. And vice versa, if we go the opposite way at the equilibrium, we have our proton donation going this way, right? So hence, there is our acid form and there is our base form. That's what I was talking about before, okay? So are those a conjugate acid-base pair? Absolutely. Now, why do these things change? You don't need to memorize what I've got in front of you here, but this is just showing you a pretty cool indicator that anyone could find. This is red cabbage, and red cabbage turns many, many different colors in different pHs of substances. Now, ultimately, though, an indicator is able to go back and forth, right? So it can start as one color, and then as you add more of an acidic substance, so more hydronium, or if you add more of a basic substance, so more hydroxide, it will force the equilibrium system to shift one direction or the other. For example, let's look at a specific indicator with bromothymol blue. Now, bromothymol blue in its more acidic form is yellow, right here. Vice versa, bromothymol blue in its more basic form is blue. So ultimately, what happens is that if you end up adding, let's just say we play around with it like this. If we add hydronium, so if we add an acidic substance, we are in theory here increasing the concentration of hydronium. Naturally, we're going to have the equilibrium shift to the left, and it's going to look yellow. Okay, now let's look at this from another scenario What if we add hydroxide? Now this looks like a little bit harder to find out. If I add hydroxide to this system, what's going to happen is it's going to naturally react with the hydronium, right? It's going to react with the strongest acid in there, okay? So if it reacts with that, then case in point, what we're going to do is we're going to decrease the concentration of the hydronium. Why? Because it's being reacted with this to form pure water. Now, if we're forming pure water, then we are increasing the concentration of water. We're decreasing the concentration of hydronium. So naturally, the equilibrium is going to shift this way to the blue side, right? To the basic side. So that's what I mean by saying, hey, this is an equilibrium system. It follows Le Chatelet's that it is going to shift in the equilibrium the way we would anticipate with concentration increases and decreases. Alrighty. Now, in terms of the step-by-step of how this works within the system, there's just a couple examples, and you guys have these in your notes that we can chat about really quickly here. Now, first things first, and again, think back to this reaction when you are considering these. Let's clear that page first. Okay, so the indicator system will do what, the bromothymol blue indicator system, when we put it into an acid. Now, this one specifically I'm mentioning, we're going to do a pH below 6, right? So not a super weak acid at like 6.5. That's practically neutral. So if I drop it into an acid, it is going to naturally experience an increase in hydronium, right? So in other words, hydronium concentration is going to go up. Fine. What will this cause to happen? Well, as a result, when we increase hydronium, the system naturally wants to react that extra hydronium, which means we're going to end up favoring the reverse reaction. Okay, work with me here. If you favor the reverse reaction, then naturally we're going to end up having this basic form gain a hydrogen, gain a proton, and change to the acidic form of the indicator. In other words, we're going to see a yellow color show up, right? It's going to favor this side. What if we do the opposite and we put a base in our bromothymol blue? Well, similar type idea, right? And we talked about this already. You're going to end up with an increase in hydroxide concentration, therefore causing a decrease in hydronium. Why? Because it will react, guys, right? Hydroxide is going to naturally react with the hydronium. Of course it is. Strong acid, strong base. When it reacts with that, we're going to form water, which will cause the forward reaction to be favored. The forward reaction is a blue color. The only reason, I'll say this again, why indicators are useful is because a color change is associated with the equilibrium. Many things undergo these equilibrium changes, but if we don't see a perceptible change, something that we can visually figure out, then they're useless, right? And bromothymol blue is a wonderful indicator, super useful. Now, there's many indicators. I'll show you a page of them in a second, but ultimately, all those different indicators have particular pH ranges that help you figure out which form of the indicator, the acidic form or the basic form, is dominating in that situation. And this is just a quick picture. I like this one that's showing you, hey, this is how a variety of different substances will have a variety of different color changes in bromothymol blue. And the thing that I want to really call your attention to is bromothymol blue goes from yellow if it is a pH range less than 6, right? And it goes to blue if it's a pH range greater than 7.6. But then we've got this middle ground, and that's what's so important. And this middle area between 6 and 7.6, that's where we end up with this greeny type colors. And notice there's a variation in green, right? But ultimately, this is color theory. Yellow, true yellow, versus a true blue. What's the mix of yellow and blue? Well, different variants of green. So please keep that in mind, hint, 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 as we look at all our different indicators, that if you end up with a pH that is in between the range, in this case, in between 6.0 and 7.6, you will also end up with color blends. Okay, have a look here at this page, guys. This is page 10 in your data booklets. And you're going to be referring to this one quite a bit for really the next bit of our podcast here, okay? Now, this is not all of the indicators that exist in the world, not at all, but it's a good list of them that are useful to us in what we're doing right now. Bromothymol blue is the one we were just discussing, and you can see within the context of bromothymol blue, there's your acid form and there's your base form listed. So that is a conjugate acid-base pair, guys. That's what's been listed for you. Range-wise, these are associated with the colors. So here's my 6.0. Anything that goes less than that 6.0 will be yellow. Here's my 7.6. Everything that is bigger than 7.6 will be blue. Anything in between will be a mix of the two. Okay, so again, let's just talk about pronunciations of some of these. The first ones are pretty simplistic. This one often throws people off. Bromocresol green. Okay, this one going over here. Chlorophenol red. I've mentioned this one before. It's a long name, but it's not that bad. Phenolphthalein, you hear it a lot. This one's very similar. Thymolphthalein. Below it, alizarin yellow, indigo carmine. And this one we don't talk very much about at all. 1,3,5 trinitrobenzene, which is not as hard anymore, considering you have a bit more knowledge about organic chemistry. Alrighty, let's put some analysis into this. This is a very similar question that you would have had in Chem 20. Okay, so consider this a bit of a review. There are 5 different indicators that were used for a solution of unknown pH, and we're trying to figure out as narrowly as we can what the pH of this solution is, purely from a qualitative color analysis. So I'll walk you through how to do this. Again, this is a review from Chem 20, but I know some of you have probably forgotten how. So first thing we do is we say, okay, we've got thymolphthalein. So we would skip over to this data booklet page again. I'm like, okay, where's thymolphthalein? Yada, yada, yada. Here it is. Great. And then we'd say, okay, thymolphthalein is from this range to this range. And those are the numbers that you want to write down by the thymolphthalein. So I'll show you what I mean. So we take it, we go, okay, thymolphthalein goes from 9.4 all the way to 10.6. And at 9.4, I'm going to write the proper color under it. It is colorless. So that means 9.4 and less, right? 10.6 vice versa will look blue, 10.6 and greater. And now we want to do this exact same analysis all the way down, guys. So I'll flip back to the data booklet just for this one, and then afterwards you can keep doing it on your own. Our next one we're going to do is bromocresol green. So we hunt for bromocresol green, yada. Oh, look, there it is, okay? We say, all right, bromocresol green, 3.8 and less is yellow, and 5.4 and greater is blue. Don't forget, we need to think about in-between colors, guys, right? So between yellow and blue, we're going to see that green. Vice versa for thymolphthalein, the one above, between colorless and blue, we're going to see everything from a super, super ridiculously light blue that almost doesn't look blue to deepening shades as we continue closer to the 10.6. All right, bromocresol green. Here we go. I'm just going to write down again. We've got 3.8 pH all the way to 5.4, associated with, I want to change my color here, a yellow to a blue under 5.4. Keep going through. Cresol red. Ooh, cresol red is fancy. So sometimes you have situations like this circumstance where there is more than one pH range associated with it. Well, that's fine. It just means that we have a range of color going on with this particular indicator, and you need to write down both of them, okay? So ultimately, there's more than one equilibrium associated here, just like it was with the red cabbage, for example. Okay, so the way that I tend to do these then is I'll take them and be like, okay, I've got my cresol red at 0.0 to 1.0, and then I also have it at 7.0 to 8.8. Like I said, you just have to write down both. And it goes from red, oopsies, if I could get my pen to work, red to yellow. Keep in mind, that means orange is in between. And then we go yellow to red over here. Okay? All right. There we go. Now, keep going. Phenolphthalein. Moving on to phenolphthalein, we have an 8.2. Come on, red. There we go. 8.2 to a 10.0 range. Super useful for bases, right? And it goes from colorless, this is a very, very common indicator used, all the way to pink. Bromothiamyl blue, on the other hand, is that one we talked about before, 6.0 to 7.6, and going from yellow to blue. All right, now here's how I analyze this next. I've got all this written down. Basically, that's the setup. We haven't actually figured anything out yet. And then I go over and I say, okay, the color of the indicator was colorless. So I'm going to highlight colorless so my brain is not confused in that 9.4. Keep going, blue. Okay, blue is the one that overtook here. Yellow, ooh, for crystal red, that means I'm going to highlight both of the words yellow. Phenolphthalein, colorless, 8.2. And bromothiamyl blue, yellow, 6.0. Done and done. Now we get into analysis. All right, here's where you got to be logical here. If thymolphthalein is colorless, it doesn't mean it's a pH of 9.4. It could be a pH of 6, guys. It could be a pH of 2. All of those would show up colorless. So all we know with any certainty is that the pH is under 9.4. That's the only thing we can be positive of. Keep going with the analysis. If bromocressyl green shows up blue, it's definitely not anything below 5.4, or we would see turquoises, bluish green, yellows, all the way, right? So that means that pH has to be higher than 5.4. We've already narrowed the range. It's now between 5.4 and 9.4. That's useful. Okay, keep on going with cresyl red. I've got 1.0 and 7.0. That means that if it turned yellow, you are guaranteed that the pH is greater than that 1.0. It has to be. At the same time, we know the pH is less than 7. Okay, also useful. Look, we just narrowed it down more. Before it was less than 9.4 to 5.4. Now we know it's more than 5.4, but less than 7. Whew, nice. Okay, phenolphthalein tells me the pH, because it's colorless, is going to be less than 8.2. Not that useful. I already narrowed it down to less than 7. Bromothiamyl blue, super useful. This is yellow. pH is less than 6.0. Now, some of you are going to be able to look at this and instantly see the range. Those of you that can't, I'll show you another way. But ultimately, we look at it and say, hey, it's greater than 5.4. It's less than 6. I'm looking at the data collectively. Boom, there's my range. Now, in terms of how can you actually see this, well, for those of you that need it, here's what I will do. You can draw yourself kind of like a line, right? Oh, I wanted that to be a better line. Come on. Let's try again. Oh, that's pretty good. Okay, so draw yourself a pH number line, essentially. And then I'll go through and I'll put down every single number that I get. So I'll start from the beginning and be like, okay, I've got 9.4. So I'm going to put that up here, 9.4. Then the lowest number I'm given is a 1. So I'm going to write that one down too, 1.0. Now fill in between. Next one below 9.4 is an 8.2. I'm just getting these from my pH interpretation. Then I've got a 7.0. It's not perfectly drawn. Live with it. You can figure it out. Okay, then I go and I've got a 6.0. And the next one I have on here is a 5.4. And that's all of them. Now start figuring out which ones you can eliminate. So this is where you go from a range. You go, okay, it's greater than 1.0. Fine. But all of these are greater than 1.0, but it's also has to be greater than 5.4. That means that this one I can eliminate because 5.4 is a more useful number. Now let's go the other side. It's less than 9.4, okay, cool, but it's also less than 8.2. Oh, I can get rid of this one then because 8.2 is narrowing the range. Then I say, hey, it's less than 7.0. Oh, I can get rid of the 8.2. I can narrow the range even more. But it's not just less than 7, it's even less than 6.0. Oh, now we can really narrow the range. So here we go, guys. It's less than 6.0. It's greater than 5.4. There's our range, right? We just narrowed it as far as we can. So the answer to this question then, when it comes right down to it, and I have run out of room to write that anywhere, so I'll just put it above here. We would say, this is how you write it, write the lower number first, 5.4, write pH in the middle, write the higher number above it, 6.0. Now put in your greater than less than symbols. It is greater than 5.4, so it eats the pH, it's a bigger number. It is less than 6.0, points to the smaller pH. There it is. Total review of Chem 20. You would have done the same sorts of questions. Now, let's put a Chem 30 spin on this. What if I say, okay, calculate the pH of a 0.10 mole per liter. hydrogen sulfide, or basically hydrosulfuric acid, right? And then predict the color. Here's the new part. We've already done that beginning type thing in past podcasts. Predict the color that chlorophenol red would have in this solution. Ooh, here's where it gets interesting. How do you predict the color? Well, you're going to have to go look at this page to do so, okay? All right, let's start at the beginning. What will happen when you put this acid into water? Well, it's going to do something based upon if it is a strong acid or a weak acid. And in this case, we're dealing with a weak acid. So I always make notes of those sort of things. Is it amphiprotic? Is it a weak acid, weak base, strong base? You got to think about this stuff. If this is a weak acid, guys, you know that it's going to act as a proton donor. Why is it a weak acid? Well, it's not amphiprotic. And if I look at my list on here, I can find it as a weak acid, right? It is located right there, okay? It's not listed as a conjugate base anywhere. It's simply a weak acid. Alrighty, so let's go through it. Step by step, H2S aqueous is going to react with water. Why is it reacting with water? Because it's in solution. That's how we even get a pH. pH relates to concentration of hydronium. pH wouldn't exist if this thing didn't ionize in water, okay? All right, equilibrium. Why? Because it's weak. It's not quantitative. Transfer the proton. It is a proton donor. So we end up with HS negative aqueous plus hydronium. H3O plus aqueous. So key thing here is what will the equilibrium concentration of hydronium be? Because that will allow us to calculate the pH. Simplistic ice table, guys, nothing new here. We're now in complete review territory of stuff that we did last week. It starts with a concentration of 0.10 mole per liter minus X. X is going to be fairly small, so we can assume the equilibrium concentration will be close enough to the initial concentration. Use it as is. Okay, on this side, these both start at a concentration of 0. They are 1-to-1 ratios. Should we add X to both? X and X. Now what? Like I said, total review of last week, guys. Now we're going to figure out our Ka right from our table, and from that be able to solve for X. Remember back over here, we said, hey, here is your hydrosulfuric acid. Then this is your associated Ka. That's what I need to know to keep going here. Create your equilibrium law. Ka is equal to HS negative concentration times hydronium concentration divided by the H2S, the hydrosulfuric acid concentration. Plug in what you know. That I'm going to put this a little higher. There we go. Okay. 8.9 times 10 to the negative 8 is from your data booklet, page 8 and 9, equals X squared over 0.10 moles per liter. Rearrange it. X is going to be equal to the concentration of 0.10. Nothing new here, guys, right? Super familiar. 8.9 times 10 to the negative 8. Number crunch. We end up with, remember, X is representative of our hydronium equilibrium concentration, right? So hydronium concentration, which is going to be 9.43 ... times 10 to the negative 5 moles per liter. Now what? Well, think about the goal of the question. Part 1 of it is calculate the pH. Yes, then we'll predict color. But first, we need pH. There's that simple, lovely formula. pH is equal to negative log of the hydronium concentration, the stuff that we reviewed last week from Chem 20 again. Negative log, plug in the concentration you got, 9.43 ... times 10 to the negative 5 moles per liter. Now you can round, because this is one of the final answers you're looking for. pH is equal to 4.03. All right, guys, step 2, where we need to analyze this from the perspective of phenol red. So look at your data booklet, find that chlorophenol red, and it is right here. Okay, so here's chlorophenol red, and here's my range, 5.2 to 6.8, yellow to red. Well, we just got a pH of 4.03, right? So 4.03 is definitely less than 5.2. Therefore, if I stick this indicator into my solution, it'll turn yellow. It is that simple, guys. Right? And the indicator chlorophenol red will be yellow. Dun, 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 dun. That example is now finished. I'll do one more with you. This one is going to be a base so that you can see as we go with a different type scenario. So check this one out. We have our OCl negative. Now, how did I know right away that that's a base, not amphiprotic, not an acid? Well, first of all, it's an anion, which is a pretty good hint right away that it can act as a proton acceptor. Proton acceptors are Bronsted-Lowry bases. Also, big thing here is there's no hydrogen, so it's not looking amphiprotic, right? Hence, it is a weak base. Is it a strong base? No, it does not have hydroxide in it. Weak base. Exact same process as before. You're given the initial concentration, figure out the pH, ding, 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 not POH, guys, be careful. And this time we're predicting color of thymolphthalein, so different indicator. So let's start going through it. OCl negative aqueous, when I have it in solution of water, right? So it's going to react with the water. It is going to act as a proton acceptor, all right? So logically then we end up with HOCl. It's no longer negative, it gained a positive. Plus we're left with hydroxide. This makes sense with a basic substance. You would get hydroxide. Let's make an ice table so that we can start to analyze the equilibrium concentration of this thing. It starts at 0.10 molarity. We would subtract an X amount of concentration. That X amount is going to be small enough that calculation-wise I can simply leave it as 0.10. Water is not included in equilibrium laws. The HOCl starts at 0 molarity, as does the hydroxide. They both go up by X amount, and at equilibrium they will be at X. Now we can't quite figure out the equilibrium law calculation yet because this is a base. So first things first is we're going to have to determine what Kb is. Kb, Kw over Ka. Now where do you get Ka? You get it from the conjugate acid, that should be a more familiar word now, on the table. So let's check it out here. Clear the page. Now we need to look for that OCl. So you got to scan and scan, get used to scanning on here, guys. That's just kind of how it works. The more that you see these pages, the more familiar that they get, right? So I usually start on the first page and look for it. OCl. I didn't find it. Keep going. Ding, ding, ding. There it is. Okay. Now remember, this is not Kb. No, that's the Ka associated with its conjugate acid, that 4.0. So we're going to use it and plug it in for the Ka. Kw, 1.0 times 10 to the negative 14. The Ka is 4.0 times 10 to the negative 8. Number crunch, we get Kb equal to 2.5 times 10 to the negative 7. Now we're ready for our equilibrium law. Create it. It's a base, hence the Kb, equals the concentration of the HOCl aqueous times the concentration of the hydroxide aqueous divided by our OCl, or hypochlorite aqueous. Okay? Plug in what you know. The Kb that we just calculated, of course, 2.5 times 10 to the negative 7 equals X times X is X squared over the equilibrium approximated concentration, 0.10. Get X by itself. See what I mean, guys? You should be hitting the point where you're like, yeah, I got this. Good. If you're feeling the repetition and you're starting to be able to just flow with it, excellent. Remember that X is representative of the concentration of hydroxide. So I'm going to now replace X with hydroxide concentration, and we just calculated it to be 1.581 times 10 to the negative 4 moles per liter. All right, can we directly get pH yet? Of course not, but I can get pOH, and then of course there's a slew of handy formulas that we can go with that. pOH is negative log of hydroxide concentration, so it'll be negative log of 1.58 times 10 to the negative 4. Whoa, what's my pen doing? Negative 4 moles per liter. There we go. Number crunch away, but don't round. pOH equals 3.8010 keeps on going. All right. Love this formula. pH equals, so easy, 14.00 minus 3.8010, blah, blah, blah. Go. And we're going to end up with, so ultimately, guys, I didn't write out the formula, I should have. This was that pH equals 14.00 minus POH, if I lost any of you, right? Okay, now you can round. We have an original concentration of hypochlorite with 2 sig digs, so my pH also needs 2 sig digs. It'll be 10.20. Now, we're still not done. A lot of people will be like, whoa, and stop there, because yeah, it's been a fair bit of work. But you still have to analyze the thymolphthalein. So keep that pH in the back of your head, 10.20. And now let's go back to this table. Hunt for the thymolphthalein. It's down here. Here's our thymolphthalein. We had a pH of 10.20. Look where this falls, guys. It's just before the 10.6. So it's not a deep, deep blue, but it's still definitely going to be blue. So in all honesty, the way I would usually label this, I'd be like blue, slightly lighter, or something like that, or a lighter blue, or light blue. Right? Slightly light. I mean, ultimately, is it going to look blue? Yeah, absolutely. It's just not going to be quite as deep. Alrighty. And there you have it, our analysis of acids and bases as indicators, right? Okay, 3 questions that you can do here, 5, 6, and 7. Make sure you take the time to do it, right? Go through things, make some sense of them. And we have one more podcast left in this course, which is crazy. Talk to y'all soon. Make sure you let me know if you've got questions. See ya.